I work at Akamai Technologies as an engineering manager. That's my day job. In the night and in the afternoon, I organize droidCon Boston, SwiftFest Boston, and some other conferences and meetup. I touched the first time Android in 2009 with pain, a lot of pain. It was Android 2.3, and now I'm having fun with Kotlin a lot, improved a lot the way we can write code, and let's get to today's agenda. So what we're talking about is a little bit of computer vision. How many of you are familiar with computer vision? Wow, will be tough. The fastest ever introduction to OpenCV, so we'll see what it is, how it works very, very quickly, and then we'll jump immediately into how to set up our Android application with OpenCV. We detect a traffic light, some driving lanes, features from a video source, and then we'll talk about why we're doing this. The problem that we are trying to solve, in fact, it's to provide a driving assistance solution to everyone, not just to people that has very expensive cars and that have a very integrated system, but to anyone that has an Android device. And guess what? Android devices are more than iOS devices around the world. We want to reduce the number of accidents, we want to monitor driving styles, we want to understand if you are in the lanes, if you have missed anything on the street, if you can park here, because if you guess here, if you can park, you will win something. And that's why we started to work on Pony Drive. It's the code name project of this project. It's everything. It's open source so far. There is a repository that it's pretty easy to find, bit.ly/pony-drive. And there is what we're doing, the slides, and feel free to fork, contribute, blame us, whatever. Computer vision. So, computer vision combines magic and science to create illusions. Do you agree with this sentence, with this quote? That's actually what it does. We have data sources as every single software, but here data sources are images, and images are not always clean. The way we clean these images and the way we process this image is known as image processing. An image, it's a two-dimensional projection of a 3D space. And digital images are simply created by sampling this continuous image into discrete elements. So basically what happens when you do computer vision, you translate a 3D world into a two-dimensional one. And you do this with camera. Camera usually get the 3D world translated into the two-dimensional one. What is very important? Images and frames. A frame, it's a single image. So if you're getting a single image, that's pretty obvious. If you're getting a video, it's simply a frame of the video, so an image of the video. And you have color image and grayscale images. The difference is the bits, the number of bits that you use to process this information. Why it's so important? It's important because the less bits we use, the more efficient we can be in processing this data. So digital images are also made up by pixels, and pixels are nothing more than a representation of the photosensitive elements that are stored in an image. Each pixel, it's a representation of the brightness of a given point in a two-dimensional scene that gets translated into two-dimensional by the camera or by other sensors. Usually the number of levels that you store by channels are 2 elevated to the b, where b is the number of bits. Why it's we got this 8. 8 it's an important number. And why? Because a reduced amount of bits give you much more speed in processing this image. Processing an image can take a lot of time, a lot of resources. And reducing the size of this image speed up your software, whatever it is, cloud-based or if it's based entirely on a device. Color images are a super rich set of information. There are information about luminance and about chrominance. However, luminance give you a lot of information that are always not needed to determine if an image, how looks an image, which are the point of interest of an image. Can you recognize the rosters? Mm-hmm. Okay, that's a grayscale image, that's a colored one, that's maybe 10 times smaller than the one on the left. That's the amount of data that you can reduce. So we usually play with grayscale images. It creates much more performance applications and reduce the complexity of your code. Whatever you do with the grayscale images, it's simpler than a colored one. The luminance in fact, provide enough information to detect the age of an image. So what you do, usually to do this very efficiently, you determine a region of interest to process. Let's say that we are talking about driving lanes. You acquire an image, the image contains trees, the street, or buildings, whatever, it depends where you are, the sky, and information that you really don't need. Usually, if you cut in half the image, you get enough information because you are catching the lines. And that's what is important. So you determine a region of interest. Then you scale this image at least 25% of the original size, and then you apply a grayscale transformation. Let's talk about code. So you read an image. This is OpenCV. So it's the C++ not super user-friendly syntax that you get when you play with OpenCV. You read an image, and you have a puppy bitmap file. If image is empty, you bark, or you do something, you handle the exception, whatever. And then you simply get the area of the image that you want. These are random numbers to make the code pretty readable. Once you have this region of interest, you can start to play with the scale. And you can determine which is the image with an 8. You apply the 75%, so you're reducing to 25%. And again, you're using the resize function of OpenCV. So you are really using a library. You're not talking about the math that is behind the scene. This is all abstracted for you. At the very end, you convert it to a grayscale image. And that's something that you can play with. One thing that I want you to notice is that here you have a reference to image, region of interest, and then when you apply these functions, almost every time, OpenCV will ask you for a source and a destination. That's most of the syntax that you see around. But images are not always very well done. So there is noise in every image. We apply whatever filter to keep the noise as lower than possible. And the noise is very random. So there are also random techniques to reduce the noise. Because the noise, it's really the electronic noise. So it's a representation of the random fluctuations of the image data. So image averaging, it's one of the techniques that you use. There is this small square that is represented here. Actually, if you apply whatever averaging technique with 2 images or 3 images, it's not changing at all. On this other image, where you have trying to detect some details of a tree, well, it changed a little bit. If you take a look at the averaging with 4 images, it's a little bit cleaner, so we reduced a lot of noise. And this is not readable as a slide, too much light, but make something from not readable at all to almost readable in the best case. This is another example. The original image, it's this one, and there is an application of Gaussian filtering. You get to the end, to something that is cleaner than this one, and it's also containing less data. Same for the pentagon. That's debatable if it's cleaner or not, but if you're interested, for instance, in the features of this image, that may be the lines, maybe the contrast, and so on, this is absolutely more clear than the first one. And this is true for everything. For instance, here you start from the original color, then you start to adjust the yellow, the red, and then you apply all together. This image contains less data of this one and more information, because every single detail, it's easier to detect. So we use these techniques to clean up our image, and we use thresholding techniques to make it easier to be understandable from a computer. That's an original image, and that's the result. The difference is very important. This is a grayscale image. This is a binary image. Binary image use only 2 colors, black and white. So the amount of data are maybe 100 times less or something like this. You still have all the information that you need to understand what is doing this gentleman. And the point is that you want a cleaner image to start to detect features. Features are information that you are interested into in an image. There is not exact definition, because there are several applications. For instance, Every time that you want to detect an object, you are interested in corners and edges. There are features detector that you can use to get that. But these are features. So all these points are determined through several algorithms that OpenCV give to you for free, and also these ones give you another idea of the point of interest that are detected. If you take a look, most of these circles are where an image is changing contrast, or where there is a change in the direction of the contrast. In fact, feature descriptors vary and contains a pattern that is where to sample points in the region around the descriptor, an orientation compensation that give you information about the orientation of this data, if it's changing the light, it's changing the color, whatever is changing. And some sampling pairs that are the logic that is applied by the feature to determine if there is a variation. There are several ways to get to this. So for instance, this is a SIT. SIT stays for, I don't remember, but that's a SIT feature descriptor. And here you are understanding that there are circles, that there are a lot of points of interest. And these points of interest are determined through the gradients and to several key point descriptors that understand where the gradients, which is the direction of the gradients. So binary descriptors are maybe the easiest one, represent everything with a 0 and 1. The brief describe an interest point with a vector of n pairs, so it's a little bit bigger, and usually it's performed getting through treating the image before with Gaussian filters and other filters. There is the orb, that's another descriptor that gives you the orientation about your pixels. And there is the BRISC, the binary robust invariant scalable key points, impossible to remember. But that's very interesting because it applies, this descriptor is built on 60 points, so give you a lot of precise information. And it uses internally a Gaussian filter to smooth this information and facilitate the processing of this information. The FRIC, fast retina key point, it's very similar to the previous one, but use an algorithm that simulates the retina system of the human eye to get this information. Let's take a look to some code, right? So, the fast feature descriptor looks complicated, but in practice, it's this one. So you are saying to OpenCV to create a feature descriptor with a threshold of 50, and to the detector to detect what? An image that you graded, and to use a vector to store all this information. If you want then to design on your a set of circles to detect what to show what the feature detected, you simply use the circle function that again come from OpenCV. So OpenCV gives you a lot of information and a lot of tools to facilitate this. But let's switch to a demo. Here we go. So let's try to overcomplicate a little bit things. And let's try to simply run this and see if you should start to see my screen. Let me scale it a little bit. Let's go to 40%. Let's go to another 40. 10. Okay. That should be good enough. I will run first the app here, and then I will show you something on code. Okay. You should recognize yourself, right? So I want to apply a feature detector. These are all the features. This is the data representation of you. And if you take a look, it's a little bit choppy and slow, but we can start to use a binary descriptor And if you see, there are more details, and it's a little bit faster, and it's a little bit more accurate. Obviously, it's missing some of the colored details, but it's pretty clear that we have a camera over there, that we have maybe some people it's detectable. Let's see if we can detect chairs. Yes, we can understand something, especially about the chairs that are at really, really close to me. So this is not complicated to be done. It's really a few lines of code. Let me show you something. So in the case of the binary, feature description, we are creating two math objects, our metrics that come from OpenCV. It's readable enough, the code, right? Okay. And then we convert the color. And if you take a look, we're really doing what we said at the beginning. We are converting everything to an RGB, to a grayscale image. Then we apply twice the Gaussian blur with different sides of the area of interest that we're searching for. And we store the difference between these two areas, and we simply apply the multiplication to the image using the Gaussian difference. The result, it's simply passed into the threshold that create a new image and return this image to us. So the only complicated things is understanding that you have to remember the step, converting the color, applying the Gaussian blur, create a difference, and then apply the threshold. 4 steps, and you're using this technique. Let's go here. And let's go back in presentation mode. So let's go deeper into OpenCV. So it's an image processing library. This should be clear enough for everyone. As C, C++, Java, and Python interfaces. Let me give you some history about OpenCV. It was originally written in C. Since 2.4 got migrated to almost to everything to C++, but what is not migrated stay in C, and the C++ it's used to build the new features to evolve the library. There is a Java and a Python interface. The Java one, it's the one that allows you to have in Android a Java syntax and simply using OpenCV. It's open source, and it's kind of easy to use and install. So why kinda? There are some steps that you have to work on. The most important thing to remember are these 5 data structure. The point, it's pretty self-explanatory. It's a point in the space, into the 2-dimensional space. The sides help me to determine the size of an area that I want to work with. We have a rectangular object. We have a rectangular object with an angle that is the one we use to determine the directions when we detect features, and we have the matrix. This math object, it's an image object that contains a matrix that represents the image. It's the key of everything. You will use almost 80% of the time that data structure. The point, it's self-explanatory, has a dot method and an inside method that help you to understand if a point is inside a rectangle. The sides return and calculate for you the area. The math has row and cols, length and width that are all integers and help you to determine the size of the matrix, and 2 parts, this matrix, has channels, so you know if it's a grayscale, RGB image, and so on, and the depth. The capabilities are amazing. You can manipulate data, you can do motion analysis, you can do object recognition, and you can do basic image processing like filtering, edge, corner detection, sampling and interpolation, and so on. You also can apply several transformations. Between this one, there is the resides that we saw in practice in the code snippet that was in the previous slides. You can extract an image patch, you can wrap an image finally, and you can optimize maps for a faster remap when you are dealing with a lot of information and a lot of images. You convert the color, you apply the threshold, and you can find the connected components inside your image. On top of this, just if you are not satisfied about the features, Gaussian blur, box filter, the filter 2D, and the separated filter 2D are your image processing filtering tools. Supported platforms. Windows. Who use Windows? Okay. Who cares about Windows? Linux. I use Linux. It's super fast on Linux. I have also a Mac machine, but it's impossible for me to work with OpenCV on Mac. On Linux, it's unbelievable. Mac OS, yeah, I told you the story. Android and iOS. So you're really writing code that can be used across several platforms when you do something with OpenCV. Because OpenCV was designed to be cross-platform. The library was written in C, and then it's portable on almost all the operating system. And I was wrong. 2.0, the transition to C++ started, not 2.4, sorry. For the most part, all the new algorithms are developed in C++, which is the difference. It's a little bit more easy to manipulate, to understand, and to look at the code. Now you should feel a little bit more comfortable, and we can start to think how to use OpenCV inside Android. Anyone ever tried to use OpenCV in Android? Okay? So this will be pretty straightforward for you. It's a set of screenshots, what you have to do in the right order to make it happening. First of all, you download the SDK. The SDK, you can find it at this URL, or if it's simpler for you, go on opencv.org on the download section. Explore the folders. What we have here? We have an APK, we have samples, so here we have a lot of samples. We have some APKs, but in the SDK, there is the native folder that is your best friend, because there are the JNI and the libs folder that contains what is really relevant for you to start integrating OpenCV into Android. You create whatever project you want. I strongly encourage to add the C++ support. It's not needed if you use the SDK, but if you want to add other features that are not supported in the SDK, if you want to use external libraries that use OpenCV, then you need to include the C++ support. Once you created the new project, you import the module, and you actually browse to the SDK Java folder that was in the SDK, this folder here. Once you've done this, you accept the default options, and you add it as a library dependency. So you select your app, you click the plus button, you go on library dependency, and you pick the Android OpenCV SDK. At this point, your app will not compile. So you go in the SDK Gradle file, and you have to be sure that you're using the same build tool versions in both of them. That will make you happy. Well, actually, this will make the Android compiler happy, not you. Then, in order to include the native libraries that come from OpenCV, you go on folders, you create a new JNI folder, and you go back in your SDK, you copy and paste all the files that you know under SDK native libs, and remove all the A files. So actually you are keeping all the .so files. You ask to Android to use the deprecated NDKs, and that's important. If you don't see for some reason the JNI directories, just open the Gradle file and comment this. In this way, this will, the folder will appear again. It's a change that got introduced with the latest version of Android. It took me 20 minutes to understand it. I'm saving 20 minutes of your time. Open the CMake list.txt file and reference the library in it. Will be super easy for you to find this line, because it's at the very end of the file. There is target link libraries, and that's how you refer to the library that you linked into the Android project. You check if it's loaded, adding a static method in your main activity, and that's it. Cool. So let's take a look to another small example and some code that is behind this. So, oops. Maybe it's better if I show you something. Okay. So this is another small example. We are simply grading scale the image. And this is done using the SDK of OpenCV. Now, I'm applying a canny filters. That's still you. And, but as you can see, here I have the information that I need for image processing. I have the lines. I can understand almost everything about you. That's a binary representation, and we're still using the OpenCV SDK. And here, that's custom code. As you can see, I can detect almost everything and almost all the important lines, and I can understand a lot about what's going on around me. So, why I showed to you this? Because we have two layers that are very important. One, it's the OpenCV SDK. This will help you to start right away. And then there is the C++ development that can use the SDK. So you are actually using other libraries, using other tools that OpenCV provide to you, and you can improve significantly the performance. Because every time that you talk with the OpenCV SDK, whatever function you're using, you are starting to use the JNI wrapper. So for every single call, you use the JNI wrapper, and there are, for the same feature that you can do, for the same, I don't want to use the term feature to don't create confusion, but for the same algorithm that you can reach, or you can create using the JNI wrapper and the OpenCV SDK, you can reduce the calls about 90% writing native C++. So that's very important. Once you get into the performances, use C++ directly and use the native support of the Android SDK for this. So what you really do to add whatever C++ code you want, once you created the scaffolding project that we discussed before, you search for a static native function that you will find into your code, and you add whatever you want from there. This is the super friendly syntax that you get from Android Studio. So actually it's saying, I'm going to be invoked by Java. That's your package, that's the name of the application, that's the name of the activity, and that's the name of the function. That's the entire signature name of the function. So in your Android code, you simply do hello from OpenCV. That's it. But in the C++ file, you will get all this thing. When you want to import your own file, so let's say that you want to add an additional file to the one that is created by default by Android, you have to start to refer the file with the name. You can, you need to specify the path that includes these files, and then you have to reference this file. This is this library. This is in the same line of codes where we used that we manipulated to add OpenCV. That's the way you are adding your native lib.c++ file into your application. There are extra steps because there is no SDK around it. You are writing it. And then you load it. It's simple. It's exactly the same of OpenCV, but here, rather than using the OpenCV loader, you are using directly the system loader of Android. Yeah, you are ready to write C++. But a little bit of, so let's think a little bit about it. The application structure is actually the same. So if you're used to write decent Android code, you keep your views separated by your presenters, or if you're using model view intent, by your model view, whatever. The important thing is that you don't start to treat your JNI libs folder as a trash can. So be very structured, give names to the things. One problem with C++ is that you have to import everything. If the function is not defined before it gets used, you get an exception, all these things. This usually brings to files that start to be massive, big, and messy. Keep this folder very organized. And when you separate the C++ files, include them in the right order in the CMake.txt. This will save you a lot of time. The wrapper is faster, so the less you use the wrapper, the faster will be the app. But don't stop to use it. The wrapper is fantastic. If you are experimenting, if you're not sure yet about what you're doing, and you're making research, through the wrapper you save a lot of complexity. You don't have to wait to the C++ to be compiled every time. It's really faster. And think about performance. So here it's comparison between Android 4 up to Android 6. And that's the Java compared to C to calculate an SHA1. So it's not so good with Android 5, but it depends. If you are simply calculating the primes number, you see that there is still huge differences, but Android 6 with the 64-bit architecture, it's almost the same. And even better, it's even more performant if you are manipulating math object in C++ using the JNIV wrapper if you're in this specific architecture. So whatever you are doing, before starting to move everything to C++, do it carefully and benchmark what you have. So one interesting thing, OpenCV Manager, it's an app that is on the Play Store that helps you to manage all the dependencies that you have. So usually what you do, when you have your Android application and you're using OpenCV, you try to include OpenCV. That's fine. If OpenCV gets updated, you have to update your app. Another approach is to use the OpenCV Manager. The OpenCV Manager will help on the memory usage. It's a trusted OpenCV library source, and update and bug fixes are distributed on your behalf. So if there is a bug in OpenCV, you get fixed by this OpenCV Manager. The application start, you try to bind to a service. If there is no service, you install the OpenCV Manager. Otherwise, you go and search for the OpenCV library version that you need. If there is no OpenCV, you install the OpenCV Manager install for you, the OpenCV library, and then you get a single flow to the application activity that it's less painful for the user.
That's awesome. Yeah.
This is helpful, but it's a separate app. So you have what you pay is that the user will install two apps, but it's usually okay. So traffic lights. We want to detect a traffic light. That's what we said, right? And let me switch up. Still readable, right? Yeah. Now we're going on the simulator. Should be super fast. Should be. It's good enough. Let's close this. So if you take a look here, we have traffic lights, and exactly around these, we got a circle. So detecting a traffic light, it's another simple operation if you use color detections. If you use let me check that I'm in the right application. Yes, that's the one. If you use the JNI wrapper, really doesn't need anything super complicated. To detect a light, you actually create a grayscale image by converting it from an RGBA1 to the gray one using the color BGR2 gray filter that is in the img proc class of OpenCV. you apply a Gaussian blur, and then you start to locate the minimum and maximum inside this image. Once you get there, you draw the circle. That's it. This other code is just to show you the demo. So really you need 3 steps. Convert the color, apply a Gaussian blur, and detect the minimum and maximum result. Here, again, summarize it. Gaussian blur, min-max lock result. You apply the core min-max lock function, and that's it. Driving lanes. You need to convert a bitmap to a matte structure. Let's say that you are getting an image from whatever source in your Android application. You convert the matte to grayscale. You apply the Kenny Edge algorithm, and you convert the matte back to a bitmap. Kenny Edge, it's a very complex algorithm. It's the one that I shown you before when everything was just black with the drawing lines. That's the complexity to which you are exposed. Simply calling it and playing with these thresholding values. If you go also online and you start to do computer vision courses, you will be surprised or disappointed. It depends on you. But these numbers really get discovered they say by training the model, but it's simply by attempting different values and see what is getting the best result when you parse the image. Now, if you want to render an half transformation is another spatial transformation that give you a set of red lines around your image. So this is an half transformation. It's something that helps you, for instance, to determine all these lines and all these points that, if you look at them, imagine that we cut the point of interest, the area of interest, in half. You are getting the information that you want. You have the left lane, the right lane, and you're getting the middle lane. The complexity, it's a little bit more, but why? Simply because I have to iterate into it. So, and I'm trying to keep the code a little bit organized. So the threshold is 20, the minimum line size is 38, line gap is 30. That's the half lines transformation that you are applying that come from OpenCV. Features detection. We saw already the demo. We can go again into the code. I can show you more code about it. But actually, that's it. And here, we're really doing something that is meaningless, because we are simply driving some circle. Demo. We got through the demo. Challenges. So the problem that you will have when you do this is that the device camera has different orientations. So whatever matte you apply can make sense to you right now, but cannot make sense when you're outside. So the unknown transformation should be applied to these data sorts, and it's pretty complicated to calculate all the possible transformation on the device. So you have to consider something for processing that is somewhere else. Every device has a different camera, so you get different informations. Well, actually, the informations are actually the same. It's the quality of the information that varies. So you have to implement a strategy to adapt to this. The camera, it's never static. It moves. And it's not to be stable enough to execute straight image comparison, because between now and maybe a millisecond after, the orientation can be completely different, especially when you're talking about something that is installed in a car. You can have a lot of information from the car itself through Android Automotive, and you can acquire environmental information. Why are they important? Imagine if it's snowing. How do you think that this image can change dramatically? Questions?
Thank you. Very nice talk.
Thanks.
Do you have any example of a combined image that has everything, like the lane detection, feature detection, and all of that?
Yes.
Thank you.
That's so. Here, these are three different transformations applied to the same images that are actually, through Kenny, are starting to detect where I am. And here, the half transform, it's exactly detecting the lanes. If you need, I can extend the demo and I can add it to the code that is online, and I can draw 3 lines for you. It's pretty simple because you already have the points. You are drawing this through the for loop that I showed before. So you can understand how the points are evolving, and you can simply isolate this and get these 3 lines.
And sorry, how does it look when you put the cars like in the lane?
Nice. I will extend the demo, and if you give me your email, I will send you a link. Other questions?
Yeah, I have a question.
Sure.
So how do you get the stack traces from some of the C++ code?
Yes. Well, that's a very interesting question. You actually get an exception and everything crash, but if you go into the Android monitor, you can understand which is the C++ function that it's crashing, and you can get a little bit of information over there. If you are doing something complex, I wouldn't suggest you to write the C++ directly into the Android app, but to do it separately with other tools and get in the command line the complete stack trace, because otherwise in Android Studio it's a little bit painful.
If you're running like a production app and then you're using either C++ code or an SDK of some sort that also uses C++, is there like any good tools you can use to... No.
That's why it's C++, it's a little bit more complicated.
Yeah,
but
okay.
Anyway, the real answer could be use Xcode. Xcode on macOS, it's one of the best tools to write C++ for me. If you speak with a C++ developer, probably will point you to Visual Studio, where you can get much more information. So usually it's 2 phases. You can start to experiment, but if you're doing very complicated things in C++, you're not developing in Android Studio, but somewhere else. The somewhere else can be Xcode or Visual Studio, and you can get more information about the stack trace. Other questions? Sure.
Thank you. You mentioned that for different cameras, you get different quality images in.
Mm-hmm.
So how do you find it affects your images, and what can you do to make them the same or to manage it?
That's one of the challenges that we're still working on, so I don't have the perfect answer. What I got so far is that reducing the size and applying the grayscale, it's enough for detecting the lanes. But for instance, we're having a lot of problems to detect the plates, because it's a different thing. So the lanes are static. The plates are another target that is moving, and we're getting a lot of difficulties over there. I will keep you posted. Sure.
How do you actually read the image? So one thing which I wasn't clear on, how do you exactly read the image? You got the image, and then let's say we applied a canny onto that, and I want to detect that, okay, it's a lane basically. So
Sure. So how I detect the images? There is in the OpenCV SDK, you can simply implement the interface camera bridge view base CV camera view listener 2. That's a fantastic name. But then into the on camera frame method, you are actually accessing to the specific frame of the camera. So you're getting an image over there. What you get here at line 121, it's already an image. And you can use, well, actually it's a frame. And then from the frame, you can get the image that you need. Does it answer your question? I understood it correctly or not?
not exactly.
Tell me more.
I got the image.
Yes.
Right now, how then I need a source of images to which I can compare this image and say, okay, this is a lane, or this is a road, or let's say there's a simple example like you see traffic lights, and
Yep.
there is sun or a moon as well, just right next to that. And how will I distinguish that? Okay, am I seeing the sun, or is it the traffic light?
Yep. Yeah. That's one example. But that's partially the answer to your question. Here, I'm passing the grayscale image and the RGB image.
Okay.
So from the from the override of the frame method, I'm passing a reference to the grayscale image and to the RGB image. And here, I'm doing a comparison between the two. That's one approach.
Okay.
Does it answer your question now? Cool. Other questions?
Thanks.
No other questions? So I want to leave. Oh, yeah.
So after you apply the, what's it called? The one with that generates all the lines, you say,
Yes.
oh, it's clear that there are 3 lines and that's the road. How do you convert all the little lines into 3 lines?
Instead of doing the for loop that simply draw everything, first of all, you cut the matrix in order to have less points to determine, and then through the direction of these points, you determine the one that are going in the same direction. These are the lines. Other questions? Cool. Thank you so much, guys. I will, if you want to be in touch, that's my Twitter account, and enjoy the droidCon New York.